That is, your inlet pressure at the inlet is 1 atmosphere. Right? And what we are saying is that your exit pressure or your ambient pressure is 76 kilopascal. This will give you 0.681. So they give you an exit Mach number equal to 0.76. Now again, let me just repeat again. You would not always have Mach equal to 1 at the exit. That only occurs when the pressure ratio is high enough or low enough, depending on who is divided by who, right? Usually, I like to look at ambient pressure divided by the stagnation pressure. If gamma is equal to 1.4, that value is 0.5283. If it's below that value, then it's choked. Then you will have the condition at 4 or below. Right? And once your pressure ratio is lower than that, what you will have is a continued expansion outside the nozzle. Okay. You will continue to expand. Okay. But usually for propulsion purposes, how it would expand outside is not so much of interest to you because that part of it does not produce any more thrust for you. Okay? Now, once you have that, you can calculate also the mass flow rate. Right? So one example we have is that if your Mach number is equal to 1, then the condition is choked. Then what you need to have is your PE over PT for airflow has to be less than 0.5283. Then your pressure in the ambient or the exit has to be less than 58.9 kilopascal in this case. Right? And if this is the case, your AE will be equal to A star if it's not equal to 1. Right? So, in that case, what will happen is that your AI over A star is equal to 1.7, and you can calculate what your A star will be. Make sense? And in fact, I jumped the gun a little bit here because really here is really not that important because if I really have this, it's going to choke, meaning that Mach number is going to be equal to 1 at the exit, no matter what the exit area is. You understand? The necessary condition for a nozzle to be choked is that the pressure ratio has to be low enough. It's not so much the area. Why is that? Yes?
Do you get more thrust out of a nozzle that is choked versus one that stops short of choked?
Then you really need to do a few calculations to see whether that is true. We will do that actually maybe on Thursday or a lecture after that. We'll proceed to the point where we can do that. Okay? Now, so if the nozzle is already choked, then you can calculate the mass flow rate. Understand? So what happened here, I really need to make a correction. So most of you then have already taken notes. Please correct this part of it so that you will have the real thing about it. So in this case, if this is the case, or this is the case, it will give you a choke condition, right? If a choke condition, this means that your AE itself is equal to A star. Yes?
Could you turn the light on the content? No, I think it's the button right here.
It's the down button on the...
When you're writing or your comments.
Okay. Sorry about that. Is this better? Okay. Is this better?
presentation.
But then you probably from here.
Yeah, it's good.
That's too fast. So, what I'm saying here is that early on in this example, what is our AE? You really need to calculate this AE, right? Then we already calculated. It's 0.626 of AI. Now, what I was doing there was, remember originally in the problem, it was not choke. And you calculate AE. So your AE is 62.6% of your inlet. So now I turn around and I said that, now with that geometry, if I lower the pressure low enough, then this AE becomes A star, right? Originally, this AE is not A star. Originally, your AE is here for the pressure that was given, right? 76 kilopascal. If I lower it to be below 58.9, I think the number, then what you will have is that your AE now is the A star. AE itself is now the A star. Right? And then you say, well, then what is it at the inlet? For example, in this case, your AI over A star is really AI over AE is equal to what? We already did it, 0.626. Then I can recalculate MI. Can I find you? 0.626. Let's look at that pressure ratio, area ratio. Oh, I'm sorry. It's not 0.626. Your AI over A star will be the flip of that.
Yeah,
So one of that, right? So that is about what? 1.6? 1.6 times 0.6 is 0.69, and that's it. 0.6. Okay, you can calculate. If it's 1.6, you go and look at here. They say 1.59 or 1.65. You probably do a little bit linear interpolation, but yeah, I will not feel picky about it because that's kind of my name, right? But they say if it's 1.6, so you say, oh, it's between these two, but it's much closer to 1.59 than to 1.65. So my number now becomes 0.40. But early on, this number, early on, when the back pressure was 76, your number is only 0.373. And this would make sense because what you have is treasure hunt. Here. Remember? Originally, let's say this is your 76 kilopascal, and you have such a line. And when you decrease it so that the maximum number is equal to what? All the pressure decreases. Right? So at the inlet, the pressure goes from here to there compared to the original condition. And how would that happen? Only if the flow velocity is higher, right? Because you have the same reservoir pressure or the same stagnation pressure. Now, if I decrease the back pressure, the flow should accelerate more, right? Wouldn't it be? So in the inlet, your velocity should be higher than the original our condition that is 76 kilopascal in the ambient. So these are all consistent, and it's consistent with Bernoulli equations. Like if I lower the pressure, the flow velocity should increase. But you say, okay, how about I lower even below 58.9? Then nothing will change anymore, because then the flow will only expand outside the nozzle. Make sense? So one way I would encourage you to rehearse this is that you can, hopefully you will have a small study group with classmates that you like to hang around with, and you constantly question each other. What about pressure is known as this? Okay, no, increases. Just looking for a fight, right? Oh, how about I increase the rate of, what is it? You should be able to be pro in any direction, and you should be able to answer. Okay? Now, questions for me. Anything that is not clear to you, you can ask.
Okay, so you said here, what you're saying is that there is really no efficiency or performance to be gained if after the nozzle's charged, right? After you achieve supersonic flow at the throat, then you can increase stagnation pressure, but nothing will change as far as thrust or
The mass flow will change, right?
okay.
Because let's say I keep increasing the reservoir pressure or stagnation pressure, and you have a conversion nozzle flow, then you will have only Mach number equal to 1 at the exit. So what changed? Now you have a more dense gas going through, so your mass flow rate is larger. Make sense? Something must be different, right? Otherwise, no matter what you do, it doesn't make any difference. Then we will be in a very confused state. I don't think we will have landed on the moon, right? Nothing changed, you know. Then how can you do that? I do this, nothing changed. Yes.
Well, I was just making sure the Mach number
For the conversion nozzle. So I have been put in this condition again and again. Now, we are talking about conversion nozzle. So I will get you to be familiar with what are the controlling mechanisms to change what happened in the conversion nozzle. After this, we are going into conversion diversion nozzle. And that will be even more confusing. Okay. So are you get ready, okay? Today, I still have 10 minutes. I will start conversion diversion nozzle, but between today and Thursday's class, you better get your conversion nozzle flow physics really very clear. Otherwise, when you come to conversion diversion nozzle, you'll be even more confusing. Okay? Now, conversion diversion nozzle. At least we get a little bit out of, okay. Imagine this is your nozzle. Or this coming from your reservoir. And then you have a conversion diversion nozzle. So here you have PT or PR, whichever you like it. Here you have PP, that's your ambient pressure. Now, let's do the same thing here. For P over PR. And let's get a few points across here. And this drawing is very important, certainly in your textbook you have it. But it's nice that you follow me and drawing it, because everything you do have an impression on your mind. One is very simple. It's kind of like doing homework. When you see the solutions, right? Hey, why can't I agree more? Great, right? We are all heroes. I understand you. You take an exam, you say, I cannot agree more with Michael Jordan on playing in the duck. How come I cannot duck? Right? The point here is that we can all appreciate truth or greatness, but we may not achieve it. And that's the fact, right? Michael Jordan, oh, great, I appreciate it. He's great, but it does not mean that you are great. Right? Hopefully you will be like 90% of it. And you have to do your practice, right? You can say, look, Michael always have 3 steps and dunk. So then you go to the coach and say, I will do this 3 steps and I can dunk. No, you cannot. You have to practice, so then you will be probably not. Now, here, let's at least have a first impression. If this point we call it 1, then we are all talking about non-dimensional stuff, right? If your bed pressure is the same as your reservoir pressure, then of course there will be no flow. If there is no flow, the pressure should be uniform throughout, right? As simple as like in a balloon, your pressure should be all the same in a balloon, right? Because there is no flow in it, right? Remember, pressure is kind of like voltage, right? If you have voltage difference, there will be currents. There's flow of electrons, right? Now, if you have pressure difference, there will be flow. Now, without pressure difference, there will be no flow. Now, if I decrease the pressure from 0.1 to 0.2 in the ambient, what will happen? Some flow will be induced. Right? Now, so somewhere, of course, by definition, in reservoir, you will have no flow. But in reality, you can have an infinite reservoir, so there will be a little bit of flow. So the flow goes in here. So this is like the inlet, right? This is the exit, and we can call this location flow for now. But flow can be A star later on, right? But let's say this is your flow. So you will have this flow that comes in here, and because you have a conversion nozzle in the beginning, you will have flow acceleration, and then you will have flow deceleration back. So your pressure would decrease in the conversion section of it, and would increase after it reaches the throat. But remember, this pressure we are talking about is static pressure, right? Because for an isentropic flow, your stagnation pressure will not change throughout the whole nozzle. So what happens is, if I decrease the pressure more to 0.3, then you would imagine that there will be more flow induced, or higher speed flow induced, right? So what you will have is something like this. And then it goes back up. Now, say, okay, I further reduce it to 4. Condition 4. Then I will have a decrease to 4. And then it recovers back. Now, I will call this condition 4, meaning the back pressure corresponding to this 4, to be the critical back pressure below which, if I decrease the flow, if I decrease the back pressure, the flow will not recover anymore. So one condition is that if I decrease to 5, the pressure just keep going down. What happened here is the bed pressure is sufficiently low so that you would induce Mach equal to 1 at the throat. Now, once mach is equal to 1 at the flow at the divergent section will just become supersonic. Right? This is what we have been talking about, being anti-intuitive to our everyday experience. But you can always say that, well, what happened between 3 and 4? It's not much different. It's going like that. There is no quantitative difference. Okay, so you can put in more points in there. You just draw more curve, right? So all we need to look at are the representative. Now, phi really makes qualitative difference, right? Because it doesn't recover anymore. It just continues to go down. However, between 0.4 and 0.5, what happened? You say, well, one recovers a steady pressure, one does not. And what happened in between? Let's say we have a point, let's call A here. Let's call it A point. A point will give you a pressure, apparently, well, the condition corresponding to A apparently will give you this condition. What happened is that you will have part of the flow being supersonic. So you will have a supersonic flow, and then all of a sudden you would encounter a shock wave. And once you encounter a shock wave, in this case we call it normal shock, meaning that the shock wave is normal to the flow direction. Okay, we call it normal shock. And for now, just trust me. After the shock wave, the flow becomes subsonic. Okay? So here, the flow will be supersonic for this section of it. I mean, for a small section of the divergent section. But then you will have a shock wave. And then it becomes a subsonic flow downstream of the shock wave. And the subsonic flow sees the increase in area, so it slows down. So it goes back to your normal life, like your everyday life. Yes.
You're saying the flow goes back to subsonic, but does that have to do with the wave, right? If it's normal or oblique?
Yeah, normal wave, yeah, normal. Normal shock wave. So for now, let's trust them. We will explain why. And then you will recover the steady pressure. Now, if I lower it yet another point, then you will have a shock wave that occurs later on. Let's say it goes back here. Let's call this point B. And if you reduce your pressure to a certain level, let's say like here, C, then you will have a normal shock wave right at the exit. Now, before we leave for today, just have this in mind. You have a supersonic flow for a small section of the divergent part of the nozzle. The flow will go supersonic. But then ultimately, when your flow goes out to the ambient, you will have to negotiate with it through different mechanisms. If my acceleration will continue to give me the pressure in the flow, for example, at 0.5, the pressure in the flow is the same as the ambient. It just goes out in a dream, right? It's kind of like you go to have a slide, you know, when you were kids, you go nice, right? You will never have a slide that is feel like this. That you only see in some of the kids, right? You would never have, you go like, out, right? But the condition of A, B, and C is kind of like, right? Because you couldn't negotiate with the back pressure, the only way for a supersonic flow, which is already here, here, or here. The only way for the supersonic flow to adjust to the ambient is through a shock wave. Right? So it's kind of like the flow is not preparing for it. And remember, because it's supersonic flow, any change downstream, the flow will not know anything. Now the condition here is that if you decrease the back pressure, you would induce the sonic flow and the flow, and then the divergent section of the supersonic flow up to a point where you would experience a shock wave, and that would allow you, the location of the shock wave would be in such a way that they would allow you to adjust to your back pressure. Now, one more point. If your pressure is below 5, if the back pressure is somewhere below here, then the flow will go out and continue to expand. Right? Now, the condition between phi and C, that's very strange, right? You said if the back pressure corresponds to point C, you will have a normal shock wave at the exit. But now if it's between phi and C, then it becomes oblique shock wave. So it's almost like if this is your nozzle, you have normal shock wave, right? And then you decrease the pressure, it becomes an oblique shock wave, oblique shock wave, oblique shock wave. And then in the limiting case, when the shock wave is about parallel to the flow, then there is no shock wave. There will be condition phi. So between C and phi, what you would have will be oblique shock wave outside the nozzle. So for example, if you have a condition D, then you will have, this is what I would draw. Oblique shock wave, give you a condition D. Okay? So we will come back and continue on this. So if you make notes, don't throw it away. We will continue. And this is the part that